In this video, we will be discussing sections 8.3 and 8.4, which begin on page 503 in your textbook. So we're going to be discussing using zero and negative exponents, as well as the scientific notation, which you should be familiar with the use of it in your integrated science class. So let's go ahead and just start off with a couple of our properties here. And the first of which is a to the 0th power equals 1 so long as a does not equal 0. So a can be any real number, and any number to the 0 power equals 1. And then we've got our negative exponents, which a to the negative n is simply 1 over a to the nth. So that negative exponent right there just takes that a to the n and tosses it in the denominator, all right, with 1 over it. Now, if you have a to the negative n in the denominator, what that negative exponent does is it moves it back up to the numerator, and you would get rid of the negative in the exponent and just throw it over 1. All right, so what a negative exponent does is tells you to take the reciprocal. So I'm going to go ahead and write that. Negative exponent is the reciprocal. Reciprocal. Alright, and then just a helpful little reminder, a to the first power equals a. So 7 to the first power is 7, 3 to the first power is 3, 1/3 to the first power is 1/3. So let's go ahead and tackle some examples here. So use the definition of zero and negative exponents to simplify. So as I said before, with 6 to the negative 2nd power, what that negative exponent does is allows me to move across this fraction bar from the numerator into the denominator, and I just take the negative part of the exponent out. So that is 1 over 6 squared. And I want you to go ahead and pause the video and see if you can complete any of the other examples. Alright, so part B, anything to the 0th power, no matter whether it's a number or a variable, is 1. And then there's a couple of different ways to show your work for part C. That negative exponent, what that tells you to do is to take the reciprocal. And then don't forget to distribute that squared exponent to both the numerator and the denominator. Square both pieces there, and you'll end up with 9/4 in the end. And then D causes a little bit of issues, because when you move that 0 to the denominator with the 7 as the exponent, you get 1 divided by 0, which you cannot do, so that is actually undefined. So let's go ahead and look at all the properties that we've gone over in the past couple of days. So properties of exponents, you've got the product of powers, where you're multiplying and the bases are the same, so you're going to end up adding the exponents. And then you've got power of a power, so you have some number or variable raised to a power, and then that's raised to a power again, where you multiply the exponents. And then you've got a power of a product, where in the inside you've got a product, any numbers or variables times each other, and if that is raised to a power, you need to make sure to raise both of those pieces of the product to that power of m. And quotient, in this case where you are dividing and the base is the same, you're going to subtract your exponents. And then you've got a power of a quotient, where on the inside you have a quotient that is raised to a power, and you need to make sure that you distribute that exponent. You raise each piece, the numerator and the denominator, to the same power. Alright, so fully evaluating these exponential expressions, we're going to be using a combination of these properties. So in this case, with part A, the base is the same, so that is at -2. And this is what I would think is the product of powers. So I'm going to end up adding the exponents here, 5 and -5. So that becomes -2 to the 0th power, or just 1. So why don't you see what you can go ahead and do with B, C, and D, and pause the video and then see if our solutions match up. So if you are looking at these solutions and your work doesn't 100% match up, that's okay, because there are a couple of different orders of the properties that you can go about it. So for example, with part B here, I could have used this negative exponent in my first step and thrown it all under 1 by taking the reciprocal. So I could have had 3 to the 3rd squared in the bottom, and then I would get 1 over 3 to the 6th. Alright, so a couple of different ways to do some things here. So if we move past just these examples with numbers, we can go ahead and utilize these properties with some variables as well. So simplify the expression, write your answer only using positive exponents. So we do not want any negative exponents in our answer. So if I go back to part D here, I did get 7 to the negative 2nd, and then I go ahead and use my property of negative exponents and take the reciprocal. So if you end up with a negative exponent, you're going to want to go ahead and move that either into the numerator or denominator, wherever it is not. So for part A here, you want to make sure to cube every single piece of that product. So that is 3 cubed, x to the negative 2nd cubed, and y squared cubed. Alright, and then you can go ahead and evaluate each piece. 3 cubed is 27. Then you get x to the negative 6th by multiplying those exponents with power to power, and y to the 6th. But it does say without negative exponents. They want positive exponents only. So 27 y to the 6th over x to the 6th is going to be your final answer. Alright, why don't you go ahead and see what you can do with the next example in part B. Alright, so you're going to want to go ahead and look at the different pieces that go together. So you've got your coefficients here, you've got your x's, and you've got your y's. There's a hidden piece of information that is the exponent of 1 in the denominator for x. So since I'm dividing, I subtract my exponents, and I end up with 2 pieces here that have negative exponents. So I want to go ahead and move those back to the denominator. I did reduce 4 over 8 to 1/2, so this is as simplified as it can get. So let's go ahead and look at one more example. In example 4, the order of magnitude of the radius of an atom is about 10 to the 5th times as great as the order of magnitude of the radius of a proton, which is about 10 to the negative 15th power meters. What is the order of the magnitude of the radius of an atom? So you want to begin with just setting it up with words, and then we can fill in some numbers. So if the magnitude of the radius of an atom equals 10 to the 5th times, so times the order of the magnitude of the radius of a proton, so the magnitude of the radius of a proton. Alright, so filling in my additional values here, I have 10 to the 5th power times 10 to the negative 15th power. And if I am to find the magnitude of the radius of an atom, I just need to use the product of powers here, and I have 10 to the 5th plus negative 15, which is 10 to the negative 10th, or how you might write it is 1 over 10 to the 10th. Alright, and that is the solution. Alright, so we can go ahead and move on to 8.4, using scientific notation. A number is written in scientific notation when it is of the form c times 10 to some power n, where c is going to be between 1 and 10, and n is an integer. So what you are typically going to see is only one number to the left of the decimal place, and then you're going to have a couple of numbers to the right of the decimal place. So it's going to be like 9 times 10 to some number, 10 to the 7th, or 2.63 times 10 to the negative 5th power, right? But it always has one place to the left of the decimal. I should not see a 34.7 times 10 to the 3rd. That is not proper scientific notation. So the exponents represent the number of places the decimal point moves from the original. If the exponent is positive, your result is going to be a much larger number. So if I have 9.0 times 10 to the 7th, what that means is I take that 9.0 and I move my decimal place to the right 7. So 1, 2, 3, 4, 5, 6, 7. And I fill in these places with zeros. So it's actually quite a large number. It is 90 million. Whereas a negative exponent is going to be a very small number, and if I make that a negative exponent, I'm moving the opposite direction to the left. Alright, so it's going to end up with 1, 2, 3, 4, 5, 6, 7, and there goes my decimal place, and then I fill in the zeros with the spaces. Alright, so that is a very small number. So using scientific notation, example 1, write the number in scientific notation. So I need to identify where my decimal place is and count until I have one integer to the left of the decimal place. So that is 1, 2, 3, 4, 5, 6, 7, 8. Alright, so this is going to be times 10 to the 8th, and this is going to be 2.675. Now, since I took a really large number and I made it smaller, I need to make sure that that exponent needs to be positive because I want to make that small number bigger. Alright, to result in 267.5 million. And then, since part B is the exact opposite, your exponent is going to end up negative. You have a really small number, and you're going to be moving it 1, 2, 3, 4 places. Alright, so this is times 10 to the negative 4th. And this is 4.86 times 10 to the negative 4th. So you're taking 4.86, and you're going to be making it smaller. Alright, so let's go ahead and look at example 2. Write the number in standard form. So standard form is the opposite direction. So standard form is what we originally received these numbers in. It is not scientific notation. So you are going to take your decimal place and you are going to move it 5 places according to the exponent. So that was 1, 2, 3, 4. And then you're going to move it one more and fill in a 0. So this is 7, 0, 2, 3, 4, 0, and then you fill in your commas. So this is actually 702,340. So why don't you go ahead and try it out on part B. Pause the video and see if our answers match up. Alright, so your solution should have come out 0.00003096. Right, so since it was times 10 to the negative 6th, I counted to the left 6 decimal places to make it smaller. Alright, looking at our next example, example 3, use order the following from least to greatest. So it is helpful to write them all in the same notation, alright, whatever that may be. So you might want to go from scientific notation to standard form in this case. So, if I were to take 9.2, this is the one that's different. So I will convert that into standard form by counting to the right 6 decimal places. 1, 2, 3, 4, 5, 6. Filling in the zeros. Alright, so that is 9,200,000. Alright, so from least to greatest goes 9,028,000, and then 9,200,000, and then 93 million. Right, that is least to greatest, and if you were to write them in scientific notation, this is 9.2 times 10 to the 6th, and you could make this 9.028 times 10 to the 2, 3, 4, 5, 6 times 10 to the 6th, or 9.3 times 10 to the 1, 2, 3, 4, 5, 6, 7. Alright, let's look at some more examples. Evaluate the expression, evaluate the expression and use scientific notation. Write your answer in scientific notation. So here I'm multiplying two numbers. What you can do is rewrite it. You can use your commutative property. You can take 5.7 times 2.6 and then 10 to the third times 10 to the fourth. And you can deal with them piece by piece. So I know that 10 to the third times 10 to the fourth is 10 to the seventh. And then 5.7 times 2.6 is 14.82. Now keep in mind that this is not in scientific notation any longer, since it is 14 and it has two decimal places. Two places to the left of the decimal. So I am going to want to move that. Alright, so since I made this number smaller, I'm going to need to make that exponent bigger. So instead of 14.82 times 10 to the 7th, this becomes 1.482 times 10 to the 8th. There's a little bit of compensation there. Now, with part B and part C, it's going to be the same usage of properties with exponents as we've done before. So why don't you pause the video and see if you can do it and see if our answers match up. Alright, so here are the solutions for part B and part C. For example 4, please keep in mind that when you're dealing with exponents, you need to make sure that exponent is distributed to every part of a product or part of a quotient, and that you're raising each part to that power. So when I did that, all I got was 5.76 times 10 to the negative 8th. I didn't have to fiddle with it any further. Whereas in part C, when I divided 2.4 divided by 2.5, I got 0.96, and in order to get it into scientific notation, I needed to move the decimal place to the right. Since I made that number bigger, that piece of the number bigger, I needed to make the exponent smaller. Alright, one more example. Example 5. The radius of a red blood cell is about 4.5 times 10 to the negative 6th meters. The radius of a mycoplasma bacteria is about 1.25 times 10 to the negative 8th meters. Find the ratio of the radius of the red blood cell to the radius of the mycoplasma bacteria. What does the ratio tell you? So a ratio really just is a fraction. So when it says red blood cell to mycoplasma, that means that the red blood cell is going to be in the numerator and the mycoplasma is going to be in the denominator. So let's go ahead and set that up. That's going to be 4.5 times 10 to the negative 6th divided by 1.25 times 10 to the negative 8th. And why don't you go ahead and do the math and see what you come out to. Alright, so if you divide and then subtract your exponents over that fraction bar, you should end up with 3.6 times 10 squared. Alright, so what does that ratio tell you? what that tells you is that the red blood cell is much bigger than the radius of the red blood cell is much bigger. It's about 300 times the size of the radius of the Mycoplasma bacteria. So find the ratio of the volumes of the red blood cell and the Mycoplasma bacteria. What does the ratio tell you? So if you were to use the formula for volume of a sphere, because this is what a cell is pretty much a sphere, right? You would probably use 4/3 pi r cubed. Alright, so you would take the radii that you have and you would cube those and you would set that into one of these formulas. Alright, and if you do all the math, which at this point I'm not really expecting you to, we're just going with general common sense ideas here. Alright, look at what's happening to the radius. Instead of having this proportion just for the radius, what's happening? It is being cubed. Alright, so it is almost like taking this value and just cubing it. What's going to happen? It's going to get even bigger. And so if you were to take the ratio of volumes, it would end up, I think, somewhere around 4 million or 46 million, something like that. So even though the radius is only 360 times the size of a Mycoplasma bacteria, the volume of a red blood cell is even larger than the ratio of the radius. Alright, so I hope you guys learned a little bit about zero negative exponents and that you can use the scientific notation a little bit easier. So if you guys have any questions, please feel free to email me or comment on the assignment on Classroom. Good luck.